Moving on to the next team, Team 1. Perfect. The floor is yours, Team 1.
All right, we're going to go ahead and get started. This is Martin Plume. I'm a BYU student studying mechanical engineering, and this is Team Halo. I'm the System Integration IPT lead. So first I'm going to give an overview of our mission, just to recap. I'll talk about our mission as well as our stakeholders. So for our mission, essentially there's a need for a flexible aerial platform to perform search and rescue operations. Our high altitude locator drone will augment the helicopter role presently fulfilled by providing additional eyes in the sky. It'll augment this by being more affordable and more deployable than traditional air assets. It'll also require fewer operators and less maintenance. In addition to that, our stakeholders are primarily the Utah County Sheriff Search and Rescue Team. Our contact is Brian Hill, who's the former president of the Utah County Sheriff Search and Rescue. Some of our other potential customers are other search and rescue teams across the United States, as well as the U.S. military and Coast Guard. It was brought up in our MCR that another potential stakeholder would be a lost hiker. However, many lost hikers have reported that they've heard helicopters fly overhead and haven't been seen, and so we decided to focus our attention on the search and rescue teams who are actually performing the operations. Next, I'm going to talk a little bit about our UAV design concept. I'll talk about how we narrowed down to a final design for our UAV, as well as what our preliminary design is currently at. I'll talk about our revised operational requirements, and finally, I'll present our flight envelope. So in order to narrow down our solution space and find a final design, our team brainstormed multiple different configurations for the UAV using OpenVSP. Next, we weighted each UAV design based on different categories. You can see in the diagram the different categories that were weighted, specifically hand launch, empty weight, manufacturability, and the rest there. After they were weighted, we took the top scoring designs, which there were 3 of them, and essentially we made a hybrid of the 3 designs to come up with our final UAV design. This is what our preliminary design is currently at. We have essentially we have a conventional tail, an elevated pusher propeller, conventional wing, which may be tapered as we move forward in our analysis to reduce the structural weight of the wings. However, currently it's essentially constant chord. We'll have an airspeed sensor locator at the front, a camera on the belly, and an external payload. The external payload will allow for greater load carrying capacity. However, it will increase the total drag. We don't see this as being an issue. Essentially, we can remove the payload for longer surveillance missions, and then attach the payload for the delivery once the person has been identified. And so, while there will be extra drag, it will only be for a shorter flight time when we're actually delivering the payload. This will be further analyzed by our dynamics IPT. And finally, we have a tail boom connecting our fuselage to the tail section. These are our revised operational requirements from the MCR. Now that we'll have our flight time of 30 minutes as opposed to the 1-hour flight time that was initially anticipated. This was dictated by the constraints of our operating conditions. We'll have a cruise speed of 30 miles per hour, which is a little bit lower than what we initially anticipated of 35 to 45 miles per hour. Our signal range will be at least 1 mile. It was previously 4 miles, and this was dictated primarily by our video transmission capabilities. We'll have an aspect ratio of 6, which is down from 10. We'll have a total takeoff weight of less than 11.5 pounds, which was previously estimated at 15 pounds, and that will allow us to hand launch it easier as well. And now we'll be initially we had thought of using an infrared camera. Now we'll be using first-person video instead, as an infrared camera is expensive for just demonstrating the concept. And so we'll be using first-person video to demonstrate the concept. A further iteration might include an IR camera if needed. In addition to that, we'll only be using 1 camera instead of 2 because of the bandwidth and weight restrictions. As far as our flight envelope goes, we analyzed our flight envelope at two different operating conditions at 4,500 feet above sea level and 12,000 feet above sea level, as that's what we're anticipating flying within. Our lower load limits were found from our 4,500-foot diagram, and we used the 12,000-foot diagram to define our limits. And we had a cruise velocity of 30 miles per hour is what we were anticipating. The load limits we found were significantly increased as our altitude increased. And because we're flying in high altitude areas, that was a significant thing to analyze and perform a trade study on. We found that our positive load factor would be 5, and negative would be negative 2.37. The values to the right there, 7.5 and negative 3.56, are the ultimate load factors, which are essentially the load factors multiplied by 1.5. Our maneuvering speeds, we found there wasn't any meaningful change within the altitude range, which gave us a VA positive of 20.18 miles per hour and a VA minus of 23.87 miles per hour. Next, I'll talk a little bit about our aerodynamics and structures. I'll talk about how we sized the aircraft, selected our airfoils, the analysis that we performed, and stability and weight and balance. In order to size the aircraft, we used the spreadsheets provided by Mr. Johnson from Georgia Tech. Our constraint sizing was basically the main constraints that were constraining to our design were the altitude that we're operating at, as well as our cruise and max velocity. From that, we were able to determine our power loading and wing loading, which you can see on this diagram to the right. Using the weight sizing diagram, our main constraints that we were balancing were our payload weight and our battery weight, as well as the wing loading and power loading that we found from our constraint sizing. We performed trade studies on basically all the variables, and those were the variables that mainly dictated where we needed our final result to be. And as a result, we found that our span would be 8.02 feet, our weight would be 11.2 pounds, have a wing loading of 50 newton per meter squared, a power loading of 10 watts per newton, an aspect ratio of 6, CV naught of 0.035, span efficiency of 0.9, and an empty weight ratio, or empty weight fraction of 0.5. As far as the airfoil selection goes, we analyzed multiple airfoils following a similar pattern to that of the structures team. Essentially, the wing airfoil that we finalized on was the NACA 4412, which has a thickness of 12%, a CL max of 1.4, and a critical angle of attack of 16 degrees. For our tail, we chose the NACA 0012, which again has a thickness of 12%, a CL max of 1.075, and a critical angle of attack of 12 degrees. Both these airfoils are thick enough to allow us to integrate servos or other sensors to operate our control surfaces. The other airfoils that we analyzed, you can see there on the right. Next, I'm going to talk about our plane analysis. We used AVL for our plane analysis. This analysis was used offsetting the wings and the tail from the nose of the fuselage, which is why those numbers are so large as far as the neutral point and center of gravity. We found a static margin of 16.4%, which is a little bit larger than I think we would want per application. We would want it between 10 and 15%. However, that'll be further analyzed as we move forward. And we have a coefficient of lift at 0 degrees angle of attack of 0.314. You can see here, this is our stability analysis that we performed using AVL. On our TREPS plot, you can see we'll be stalling likely at the root, which is ideal for this application as it will prevent a rolling movement that might be induced if we stalled at the tip. Some of the key values that were found from our stability analysis were a roll of 0, a pitch of negative 7.432, yaw 0, aileron is 0 for our trimming, elevation angle of negative 10.3, and our rudder's at 0, and that was with an angle of attack of 5 degrees. As far as our weight and balance goes, this is a side view of our aircraft. Because we don't have a 3D model completed yet, this will give you an idea of where our components will be located within our plane. The fuselage center of gravity basically accounts for all of the internal components of the aircraft, the avionics and the propulsion system. The frame center of gravity includes the wings and the tail section and the fuselage. And you can see here that it gives us an entire length of our plane of a little over 6.5 feet. You can see where our components will be located relative to one another in this plot here.
All right, good morning, everyone. My name is Anthony Smonty, and I'm an aerospace engineering major at Tuskegee University. I'm going to be talking about our propulsion system, some of the trade studies that we did, and the two motors that we narrowed it down to, our propeller trade studies, as well as our preliminary selection for our ESC, prop, and motor and battery. So the two motors that we looked at heavily was the Scorpion S2 and the Hacker A50. As you can see, they both had roughly the same. We got these motors from MotoCalc based off of our preliminary design constraints. Both of them have roughly the same runtime of 47 minutes. The Scorpion had a little bit better motor efficiency of 89.4 as to the Hacker's 86.7%. RPMs, as you can see, 4,200. Airspeed roughly the same, and thrust roughly the same across both motors. One thing that really stood out to us about the Scorpion is that lower airspeeds, the motor efficiency was much more constant than the Hacker, as you can see on the graph for the blue line. The Hacker's a little bit more consistent across the board, the Scorpion's a little more consistent across the board, and the Hacker's it comes up and then it drops back off as we approach 25 miles per hour. So when we started with the propeller, which one we're looking into, we took into account the propeller pitch, the diameter, our motor efficiency, our flight time, as well as our thrust. Based off these graphs, we found that our main findings were that as there was a steeper increase of efficiency with an increased diameter, and there was the larger diameter gave a larger thrust. And based off of this, as well as from the MotoCalc calculations, the Scorpion was a little bit more efficient, and that's what we were looking for as far as airtime based off of weight, because one of our original issues was that we were too heavy, and if we can have a little bit more efficiency and still be the same across the board between the two engines, we'll take the more efficient one. So our preliminary for our preliminary selection, we went with the Scorpion S2. Obviously, it's a little bit more. It's the more efficient one. It's got the adequate thrust to get our drone into the air. Flight time, that's great RPM, 330 per voltage constant, and it weighs less than a pound. Again, going back to that weight, just being as light as possible so we can still get into the air. For battery, when we went with the CoCam 3200 SHD battery, max continuous current of 75 amps and a max continuous power of 2,000 watts. For the ESC, we just went very simple, enough to get the job done, which was the generic OR88 6S brushless ESC. Nothing super special about it, but it doesn't have all these different gadgets on it. It'll get the job done. And then for the prop, we went with a 16 by 8 inch prop, most efficient as far as being paired with this motor, and then gives us thrust to get our drone into the air.
Hi, my name is Alex Sells. I am an aerospace engineering student at the University of Washington, and I'm going to be discussing the avionics block diagram, systems, and our payload for this mission. So here's our block diagram, which includes the powertrain of the battery, ESC, and motor, as well as the brains, our PICTOC 4, and additional sensors like our radio, GPS, and then a receiver to control servos, which control our control surfaces. What's special about the PICTOC 4 is that it has 2 accelerometers, 16 PWM outputs, and a 32-bit processor. It's simply the best flight controller on the market that you can buy. And so by spending money on this system, we save ourselves a lot of time in terms of setting up our own environment to control our aircraft and a lot of compatibility problems. Additionally, our radio is a Holybro V3. It's great because it is compatible with the Pixhawk 4 directly, which means that it's also configurable through Mission Planner, which is the software that is used to control autonomous flight. And it's in the 900 megahertz range, which means it's within the realm of hobby aircraft and doesn't require a special license. For our GPS module, we chose the Pixhawk 4 GPS module. It simply has the highest sensitivity on the market that we could find. It has a small form factor, and it's directly compatible with the Pixhawk 4, which saves us time and energy trying to get these systems to interact with each other. And a little bit more on our battery. It's a 4-cell LiPo, which since our motor is rated for a 4S motor, or it's a 4S motor, that's the proper voltage that we need to supply it, and it's very energy dense, which is great for endurance flying. So our payload is essentially a camera system, which we're using the RunCam Micro Eagle. That's going to take all of our video and we'll send that to the Luminaire transmitter. Transmitter is going to send that out from our aircraft amplified by a Luminaire antenna. On the ground, the patch antenna is going to hook up with our receiver, allowing us to take the signal from our aircraft and translate it into a video signal on our ground station. So an operational review of our team over the past couple of weeks. We'll go talk about costs, some risks, and our schedule going forward. So for our current budget, we're planning on $2,100 to make our entire aircraft. Accounting for some other spare parts, we still have about $3,000 unallocated. This means any financial overruns are likely to be safe, and we don't need to worry too much about overrunning our budget and have the possibility of either making a secondary aircraft if we have revisions late into the process and or other problems that will arise. So all the IPT leads came together and created an Excel sheet with all of the risks that could happen to our aircraft. Full details can be provided at the end, and we won't spend too much time going over them individually. However, we did throw everything into this risk matrix where red is high risk, yellow is medium risk, and green is low risk. For the risks that we established, most of them are medium risks, which means that they're with the proper safety procedures and the proper planning beforehand, all of them will be solvable and should not provide any sort of hindrance to our ability to complete the mission. For our main risks on each department, we have a structural failure, and the way that we'll mitigate that is to just make sure everything is tested in simulations and hope that we have sufficient factors of safety. Operationally, the main factor is a stall. In order to combat that, we're designing our aircraft to be able to fly at a lower angle of attack than our critical angle of attack, which will prevent the aircraft from entering the stall regime. Analytically, we could underpredict the thrust. In order to prevent that, we're using MotoCalc to carefully analyze all of our motor and propeller choices, and then also make sure that we have an overpowered aircraft in the event that we do, in fact, underpredict how much thrust we're going to have. And financially, our biggest risk is going over budget, and we're going to prevent that by having all of the IPT leads come together and know what our current budget is, and work with our project managers to make sure that the parts that we're ordering are actually the parts that we need at the price point that we're buying them at. So reviewing our performance, we fell behind in a number of key areas over the past couple of weeks. What we learned from that is that we need to make our communication more efficient, keep track of who is doing what tasks, and making sure that we follow up with them to make sure that the tasks are being completed in a timely manner. Currently, we're on schedule, and we have met with Everett Community College to discuss their manufacturing capabilities to help influence our design decisions going forward. So for our upcoming schedule, we are going to develop and test the camera system using a pre-bought UAV. This way we don't have to put our actual UAV into production that early, and our electronics can be verified before they go on it. We need to model the airplane and the internal parts of our aircraft in 3D Experience. We need to do computer simulation and scale testing of our model to ensure that the numbers that we're predicting are actually accurate. And then we need to continue to communicate with every community college to coordinate our designs to be compatible with their manufacturing capabilities. And we also need to design and build a prototype glider by the end of this term. Any questions?
Are there any questions for Team 1?
Bronco Luckett from Boeing. I have a question. I would like to actually see if there are any available details about how is the camera integrated with the fuselage. Is the camera by itself sufficient? Do you guys need any gimbal mechanism? How are you providing the line of sight? If any of these details are available at this time. The way the fuselage looks like right now, it's difficult to judge that.
The camera is going to be viewing outside the belly of the aircraft. We're not going to have it gimbaled. It does put it at a little bit of a risk of when the airplane banks, we may not get the field of view that we are looking for. But it's going to be viewing directly underneath the airplane and shouldn't be obstructed by our payload.
Hey, this is Greg. Could you just really quick go back to slide or forward to slide 18, please? So through slide 17, 18, and 19, and this just might be an error on the slide. It seems that the hacker motor is more efficient by a significant margin. But the decision on slide 19, if you can go forward, is to go with the Scorpion motor. Is that correct?
Yes, sir. You back to slide 18. Thank you. Yes, apologies, that is a typo.
Okay. All right. Thank you.
Welcome.
Are there any more questions for Team 1? Okay, we finished a few minutes early.
Thank you for listening to our presentation.
Okay, so we're a little bit ahead of schedule here, so hopefully it takes a little while to transition into Team 5. But we would ask that Team 5 get ready to share. Again, reminder about Qualtrics survey feedback. So far, this has been great to hear this. The team's responses have been good. And thanks to the questions that they're getting from subject matter experts. We do appreciate that. Team 5, if you would like to share your screen. Caladrius.
Hi, I was wondering, where is the screen share option?
If you go, are you using a Mac or a PC?
PC.
Okay, you should go to, if you're on your WebEx meetings account, are you accessing this through a web browser, or have you downloaded the app?
A web browser.
That may be the problem. If you're doing it only through a web browser, you will likely not be able to share your screen.
Okay. Okay, 1 second.
Yeah, we have some backup plans, maybe. you send me the PowerPoint, I certainly can present it and share the screen from here and have you talk wherever you may be. Or if you have another member of your team that has PowerPoint, they could share their screen as well.
All right, can you see my screen?